foundations must carry the loads of the building and transmit them safely into the ground. Any settlement must be sufficiently controlled to minimise building distortion and cracking. The load of the walls, roof and floors are known as the dead load. The loads of the occupants, furniture and snow are known as the imposed load. Most houses have strip foundations. As the name implies, this is a strip of concrete supporting the load-bearing walls. The width of the strip depends on the nature of the ground and the load of the building. Thousands of Victorian houses, particularly those built by speculators, were built without concrete foundations. The load-bearing walls were sometimes built straight onto the ground in shallow trenches, or perhaps on a level surface of compacted ashes or stone dust. Bigger, better quality houses often had brick or stone footings. Here, the additional brickwork at the base of the wall spreads the load across the ground. Foundations can fail if they are incorrectly designed or built. They can also fail through unforeseen ground problems such as earthquakes, flooding, or mining subsidence. This church tower in Bristol is 1.5 metres out of plumb. The first two stages of the tower were completed in about 1400 and started to lean shortly after because the alluvial soil was too weak to support the heavy load. Inside the tower, a buttress was built to try to halt the lean. The upper stage, built at a different angle in an attempt to straighten it, was started in about 1460. The Leaning Tower has been a tourist attraction ever since. Before foundation design and construction can begin, extensive site investigation is required. This normally involves three basic stages. The first is a desk-based study using existing documents, maps and photographs to help determine the history and conditions of the site. The second stage is a walkover survey, giving the designer the opportunity to identify the nature of the ground and any potential hazards. On greenfield sites, the most significant features might be water streams, public footpaths, trees and pylons. On this city brownfield site, a previous lead works, there are many more factors to consider. The water table might be quite high because the site is located next to a river. The site's previous industrial use could mean the ground is contaminated. The site probably contains old foundations and services. There's also an electrical substation on the site, and of course, adjacent buildings. To cap it all, the Shot Tower is a listed building. A direct ground examination is the third stage in the site investigation. This site, currently a local authority car park, is being developed as medium-rise flats. A specialist firm has been contracted to take a number of ground samples across the site and produce a detailed report for the architects. Boreholes help determine the nature and thickness of the strata and will also provide information on groundwater levels and other hazards in the ground. The samples are carefully recorded, boxed up and taken away for further analysis. Another method of ground investigation is to dig a series of trial pits. This is the most common type of investigation for low-rise housing, particularly on greenfield sites. It's also common where there may be items of archaeological interest. This Victorian road has been photographed and recorded by the city archaeologist, but wasn't deemed to be of particular significance. Work was allowed to proceed. The trial pits to assess the ground conditions don't normally have to be deeper than 4 to 5 metres, unless specific problems are encountered. Samples of subsoil can be taken away for analysis, and engineers can determine the nature of the various strata by inspecting and measuring the sides of the pit. In the UK, there are a number of different types of subsoil, each with its own characteristics. Their bearing capacity, in other words, the loads they can safely carry, will vary. Stable solid rock has a very high bearing capacity and can easily carry the loads of housing. Excavation can be difficult, but in most cases a concrete foundation is not necessary. The rock only has to be levelled, ready for the bricklayers. Loose rock, providing it's stable and of a consistent nature, can also provide a good foundation and is obviously easier to excavate. Gravels and compact sands mostly have a good bearing capacity, although in ground with a high water table or running water, the finer aggregates may be washed away. Chalk subsoil can provide a good foundation. It's quite hard and difficult to dig, although it can deteriorate and soften if it gets wet. It's also susceptible to frost heave. Clays have a wide range of bearing capacities and also vary in colour. Their stability and overall strength are affected by their moisture content. Firm clays and stiff clays are ideal for simple strip foundations. This road, crossing the Somerset Levels, has subsided because it's built on peat. Peat is an organic, fibrous material with a high water content and very low bearing capacity. It's black or brown with a distinct odour. Peat shrink and swell considerably, and their high compressibility leads to high settlement. It's best avoided as a foundation. Despite ecological concerns, it's much in demand as garden fertiliser. The ground on former industrial sites may contain all manner of materials, some of them hazardous. They'll often require specialist investigation and complex foundations. With the exception of peat and soft clays, most subsoils are suitable for strip foundations. A table in the building regulations gives minimum foundation width for specific loads and subsoils. In simple terms, a single-storey house on compact sand will require a foundation at least 300 mm wide. A higher building, or weaker ground, will require a wider foundation. If the buildings are more than 3 or 4 stories high, or if the ground is of low bearing capacity, the foundations will have to be designed by engineers. Most houses are built with strip foundations, but whatever the foundation type, the first stage is to remove the topsoil, typically 150 to 200 mm thick. This organic material can be taken away and sold or stockpiled for future use. The centre line of the foundation trench is set out for the digger drivers. Foundations are normally required under all the load-bearing walls. The foundations under any internal load-bearing walls may sometimes be slightly narrower than those under external walls. On this site, the ground is a stiff clay, and the foundation width only has to be 450 mm. The excavation, therefore, has to be very accurate to ensure that the 300 mm wall sits in the centre of the foundation. The depth of the foundation depends on the characteristics of the soil. In clay soils, for example, the moisture content will vary depending on the season. This affects the ground to a depth of about 1 metre. In long, hot periods, the ground will dry and shrink. In long, wet periods, the ground will absorb moisture and expand. This expansion and contraction is rarely even, and differential movement will inevitably cause cracking. Some chalks and fine sands are subject to frost heave. In wet, freezing conditions, the ground near the surface expands. In these soils, the foundation should therefore be at least 600 millimetres deep. Once the trenches have been dug, they should be concreted as soon as possible. Open trenches are dangerous, and there's always the risk of the sides falling in. Short pieces of pipe provide a duct to carry services across the trench. Concrete can be batched on site, although most builders prefer to use ready-mixed. Concrete is a mix of cement, fine aggregate and coarse aggregate. By varying the mix proportions, its strength can be altered. The addition of water allows the chemical reaction called hydration to occur. This binds the cement and aggregate together and hardens the concrete. The correct amount of water is vital. Too little and complete hydration will not take place. Too much and the surplus water not required for hydration will evaporate and leave behind tiny voids. This will weaken the concrete. The surface of the concrete is tamped level, ready for the bricklayers. Traditionally, a strip foundation comprised a strip of concrete in the bottom of the trench. Bricklayers working at foundation level would then build the brick and block walls. But in good ground, where foundations can be narrow, working space for bricklayers requires extra excavation. To protect the bricklayers, the trench sides may also have to be supported. Nowadays, ready-mix concrete is readily available and often cheaper than blockwork, so it's often quicker and more economic to fill narrow trenches with concrete. Where foundations have to be wider than 600 millimetres because of the bearing capacity of the ground, trench fill may become too expensive. It's often cheaper to provide traditional strip foundations. A disadvantage of trench fill is that service ducts below the concrete need to be carefully planned. Mistakes can be expensive to rectify. In traditional foundations, service openings are formed in the blockwork. Their position is easy to change. Foundations have to be laid level, and on sloping sites, this can lead to a lot of excavation and expensive earthwork support. Trying to slope the foundation to match the fall of the ground is obviously not an option. To keep the excavation to a minimum and to ensure a level surface for the building, the foundation can be stepped. The building regulations contain a number of rules to ensure stepped foundations are correctly constructed. These control the height of the step and the overlap. The load from the walls is distributed through the concrete at about 45 degrees. In thin, wide foundations, there's the danger that the load from the wall can crack the concrete, reducing the effective bearing area. This is called shear failure. As long as the thickness of the concrete is not less than the projection, the correct bearing area will be maintained. In wide foundations, this uses a lot of concrete, so a cheaper option is to keep the foundation thin, but reinforce the concrete with steel. In clay soils, trees near buildings can cause problems. Roots can extend a considerable distance and draw lots of water from the ground. In long hot summers with low rainfall, the tree continues to draw water and the clay will shrink. Cracking in the foundations and walls may occur. Developers should remember that little trees soon become big trees. Once the root zone reaches the foundations, they are at risk. Building settlement is rarely even and cracking will occur. To avoid this failure, new trees must be kept well clear of the foundation, usually at least a tree's mature height. Where there are groups of trees, this distance should be increased. In clay soils, chopping down trees causes the opposite problem. As the ground slowly regains moisture, it will expand. If trees are cleared and houses are built on the site before this ground expansion is complete, cracking will occur in the walls and foundations. In clay soils, problems of shrinkage and heave can be avoided by using deep strip foundations, but there are cheaper solutions. This prestigious housing development in Berkshire is being built on wet, marshy ground. Strip foundations are unsuitable here, so reinforced concrete piles are being used instead. Piles transfer loads through weak or unstable soil to deeper soil of higher bearing capacity. A reinforced ground beam sits on top of the piles and distributes the load from the walls. In granular soil, such as sand and gravel, end-bearing piles can be used. They're usually driven or forced into the ground and are sometimes referred to as displacement piles. They can be formed in a number of ways. In clay soils, piles rely partly on end-bearing, but mostly on friction between the pile sides and the soil. They can be formed using replacement piles, where the ground is first removed by boring or augering. Piles can be used on shrinkable clays where existing or felled trees are close to the foundation, where minor obstructions in the ground make trenching difficult, where a firm stratum is at too great a depth for strip foundations, and where a high water table will make trenching impractical. On this site, formerly a power station and working docks, the ground contains a lot of filled material, and at various depths, outcrops of rock. The water table is also high because the site is next to the quay. Precast reinforced concrete piles were chosen for this site. It was the engineer's view that these offered the fastest and cheapest solution. Site investigation suggested that pile depths might be between 10 and 20 metres. The piles are driven into the ground by a crane-mounted drop hammer. As the pile reaches a firm bearing, it becomes harder to drive. Design calculations showed that adequate support would be achieved when 10 hammer blows couldn't drive the pile more than 10 millimetres into the ground. This is known as the set. Where obstructions in the ground forced the concrete piles out of position or broke them, stronger but much more expensive steel piles were driven alongside. The excess lengths of pile were bitten off with hydraulic jaws mounted on the back of a JCB. Further trimming was carried out by compressed air tools to expose the steel bars in the piles. Driven or displacement piles can also be formed with in situ concrete. One common method is to drive a steel cylinder with a plug of concrete in the bottom to the appropriate depth. At this point, the cylinder is restrained and continued hammering pushes out the concrete plug. In situ concrete is poured in and the steel tube removed. A steel cage is dropped into the wet concrete to complete the pile. Augured piles are suitable for many types of ground, particularly clays. They're replacement piles. In other words, the ground is removed and then replaced with reinforced in situ concrete. They're much quieter than driven piles and produce little ground vibration. However, there can be a lot of excavated material to cart off site. The auger has a hollow stem. Once the pile has reached the correct depth, determined in advance through site investigation, concrete is injected down the stem and the auger is slowly removed. To withstand horizontal and bending loads, the pile is reinforced, sometimes with a steel cage, sometimes with a single steel bar. Spacers on the cage keep the reinforcement bars within the concrete. The steel projects from the top of the pile and provides a good connection with the steel cage forming the ground beam. The walls of the house are built onto the ground beam, which transfers the loads into the piles. This may look similar to a traditional strip foundation, but the ground beam, despite its name, spans from pile to pile and is not supported by the ground beneath it. This permanent polystyrene formwork acts as a compressible layer and is sometimes used in clay soils to prevent possible expansion of the clay cracking the beam. It may be required underneath or either side of the concrete. This piling system is quite unusual in that it is a bored displacement pile. Most bored piles are replacement piles. During boring, the ground is compacted as the rotary head drills into the ground. The advantage of this pile is that there's minimal cart-away, and unlike displacement piles, it's quiet and vibration-free. At the appropriate depth, concrete is pumped down the hollow shaft while it's withdrawn from the ground. In most ground conditions, this is an alternative to augured piles. On some sites, raft foundations may be the best option. A raft foundation spreads the building load over the whole ground floor area. In the 1940s and 50s, raft foundations were quite common, particularly beneath the thousands of prefabricated concrete or steel houses built after the Second World War. Most of these houses were built on greenfield sites with good bearing capacity. On this type of ground, rafts were relatively cheap, easy to construct, and didn't require extensive excavation. In those days, foundation trenches were usually dug by hand. Reinforced concrete rafts can also be used where there's a risk of subsidence. They're quite common, for example, in areas of present or past coal mining. They can also be used on very soft clays or compressible fills where the depth of a firmer stratum precludes the economic use of strip foundations or piling. The design of the raft will vary to reflect the specific site conditions. Rafts may need perimeter and internal ground beams to make them stiff enough to prevent differential settlement and subsequent distortion of the superstructure. Nowadays, rafts have to be designed on a one-by-one basis. In other words, there are no deemed to satisfy provisions in the building regulations as there are with strip foundations. Rafts have also been used successfully on sloping sites as an alternative to traditional stepped foundations. A well-compacted granular fill can form a suitable base for the raft. Raft foundations are comparatively rare. They require specialist design, and many house builders, wherever possible, prefer tried and tested strip foundations.